Hello, everybody. I hope you're doing well. Welcome to another video reviewing your probability and statistics fundamentals. It's so great to be with you today on a Friday evening. And today in this video, we're going to be continuing our discussion of confidence intervals. So as you recall in the previous video, we've discussed the intuition behind how a confidence interval works. And we've also studied how to use confidence intervals to provide some sort of estimation with some degree of certainty as to the population mean. We're going to shift gears and extend this concept, but talk about population proportions, right? So now, given a sample where you can find a proportion, how can we use that sample to estimate to some degree of certainty the true population proportion based on the problem you want to study? So, as you recall in our video on confidence interval, a confidence interval consists of a starting value plus or minus some margin of error, right? And the margin of error is influenced by the sample size. It's also influenced by our confidence level, and it's also influenced by our standard deviation. So the start value, in this case, our proportion would be some idea of the sample proportion. We'll call it p hat. And the margin of error is essentially the z star multiplied by the standard deviation of the proportion, or it could be t star multiplied by the standard deviation. So in the case of sampling distribution of proportions, our sample proportion here is represented by p hat right here. And this term in red is representing our margin of error. So this area right here, this is our z star. This is in the case where we can assume normality. And as you may recall, when we talked about sampling distribution of proportions, this term in blue represents the standard deviation for sampling distribution of proportions. So you can see how these three pieces come together. So the red is representing our margin of error. Black is here is representing the sample proportion. So this is like our statistic. The z star is representing what we call a test statistic. So that will be usually either z star or t star. So this is our test statistic. And the value here in blue is the standard deviation for a sampling distribution of proportions. Okay, so now we have this backbone built in. One thing to note about this formula is this formula uses z star in the case where we assume normality, but we can use t star and essentially replace this z star right here with the t star if we don't assume normality. So as you may recall, our normality checks for sampling distribution of proportions are the following. So np hat must be greater than or equal to 10, and n times 1 minus p hat must be greater than or equal to 10. This is our check to see for normality, as you may recall in our sampling distribution of proportions video. If this is new to you, I would recommend going back to that video to make sure you understand sampling distribution of proportions before you come into talking about confidence intervals. So with that, without further ado, let's get started on the example problems. So example 1, we want to estimate the proportion of teenagers that get at least 8 hours of sleep, because sleep is important and health is important. So you collect a sample of 70 teenagers and find that 30 of them get at least 8 hours of sleep. Construct a 99% confidence interval to estimate the true proportion of teenagers that get at least 8 hours of sleep. Okay, so for example 1, what do we know? We know our sample size is 70 teenagers, right? We also know that the confidence level is 99%. And we know 30 out of the 70 get at least 8 hours of sleep. Okay, so we want to construct a confidence interval estimating the true proportion. So let's do a quick normality check. So we know our sample proportion, 30 out of 70 students said that they get at least 8 hours sleep. So the p hat is 30 out of 70, right? So we know that n times p hat equals 70 times 30 over 70, which equals 30. which is greater than or equal to 10. We also know that n times 1 minus p hat equals 70 times 1 minus 30 over 70, which equals 70 times 40 out of 70, which equals 40, which is greater than or equal to 10. So normality passes, right? So now we can use the z-statistic to approximate our sampling distribution of proportions. So our confidence interval, we'll just simply use this equation right here, right? So the confidence interval is going to be equal to p hat plus or minus z star times the square root of p hat 1 minus p hat over n. Okay, so now all we have to do is just plug in the terms. So we know p hat is 30 out of 70, right? We also know that z star is represented or is related to the confidence level of 99%. So as you may recall in the previous video, confidence intervals generally contain a starting point and a margin of error, and thus we have this type of area here. We know that the area between these two vertical bars here, this is 0.99. So what we want to do is we want to find the z-score, z naught, such that the probability that z is less than or equal to negative z naught equals 0.01 divided by 2. And this is due to the symmetric nature of the normal distribution, right? So this area here is 0.01 divided by 2. And this area here is 0.01 divided by 2. So all we have to do is use our z-table to find this target z statistic. So we go into our table. We know that 0.01 divided by 2 is 0.005. So we look in our table and look for the area where we have 0.005. And we see that happens right here with the z-score of negative 2.57, approximately. So we know that z star is approximately 2.57. So that means we know that the z star is 2.57. And then we can take the standard deviation of the sampling distribution and proportions by plugging in p hat. So we know this square root term is going to become 30 over 70, 1 minus 30 over 70, divided by our sample size is 70. So now all we have to do is punch this into the calculator, and that should give us the confidence interval that best approximates the true proportion of teenagers who get at least 8 hours of sleep. So I'm going to take a moment to punch this into your calculator. You should follow along as well. So it looks like our interval comes out to be approximately 0.277, comma 0.581. So this is our confidence interval estimating the true proportion of teenagers who get at least 8 hours of sleep. So this problem doesn't sound too bad. It's all a matter of really using this formula and basically getting all the terms you need, and you just simply make a substitution. All right, we move on to example 2. So what does example 2 entail? We want to estimate the proportion of chairs that contain a defect in the factory. Due to overhead in inspecting a chair for a defect, you're able to inspect 15 chairs. Among these 15 chairs you inspect, 7 have a defect. So we want to construct a 90% confidence interval to estimate the true proportion of chairs that contain a defect. So we repeat the same process. We know that the sample size is 15. We know that 7 out of 15 have defect. And we know that the confidence level, in this case, is 90%. So what do we know from this? We know that p hat is 7 over 15. So we can do our normality check. We run n times p hat, which is 15 times 7/15, which is 7, which is less than or equal to 10. We also check n times 1 minus p hat, which is 15 times 8 over 15. And that's going to be 8, which is less than or equal to 10. So normality check fails. So, unfortunately, we aren't able to use the z-distribution to approximate the sampling distribution of proportions, right? So, because the normality check fails, we have to use the t-statistic, right? So, what do we need for our t-statistic? Well, we know that in our t-distribution, this area right here, shown in red, is 0.9, right? So that means this area here in green must be 0.05, and this area here must also be 0.05. So if we have this T naught here, we want to find the probability that T less than negative T naught equals 0.05, and we want to find the T naught that accomplishes that. And due to the symmetric nature, we can even find this probability if it's easier, right? So we go into our t-table, right? And we look for where this area here in gray is 0.05. And we also know that since our sample size is 15, we know that the degrees of freedom is 14, right? Because 15 minus 1 is 14. So what I'm going to do is I'm going to go into this table, right? Go to the row where degrees of freedom is 14, and I'm going to look for where this value here is 0.05. So degrees of freedom of 14, go to 0.05. 1.761 is our t-score, right? So we know that t star equals 1.761. So now to construct a confidence interval, we simply use this formula here, except we replace z star with t star, right? So the confidence interval becomes 7 out of 15 plus or minus 1.761 times the square root of 7 over 15 times 1 minus 7 over 15 over the sample size of 15, right? So now all I have to do is just punch this into my calculator and we'll get our interval. So the interval will become So the interval will become approximately 0.240, comma 0.694. So this is our estimation of the true proportion of chairs which contain our defect in our factory. All right, so this should be pretty straightforward. It's just a similar application, except we're using the t-statistic instead of the z-statistic, so this should be relatively straightforward. We move on to example 3. So example 3 is a little bit interesting. So we want to estimate the proportion of voters who support a new bill in your state, right? And we want to estimate this proportion within 3 percentage points of accuracy. So we want to use a conservative estimate, right? Because we don't have prior data on voters who support this new bill, right? It's a brand new bill that has been proposed in your state, and your state is the first to propose it. We're going to assume that half of the voters support the bill, half oppose, which is a conservative estimate, right? Because we don't really have prior data. So we're going to be conservative in our estimation, right? So our goal is to find the sample size needed to achieve an estimation of the true proportion of voters who support the new bill within 3 percentage points of accuracy, right? So what do we know here? We know that the margin of error, right, is 0.03, right? Because we want to estimate the true proportion within 3 percentage points of accuracy, so we can go plus or minus 3, basically. And that corresponds to the margin of error term. So the margin of error equals 0.03 because 3% is 0.03 as a decimal. We will also use our conservative estimate. So p hat is going to be 0.5 because we assume 50% of voters support the bill while 50% oppose the bill. And we also know that our confidence level is going to be, in this case, I'm going to use the confidence level of 95%. I know I didn't type it in the question, and I'm sorry that I omitted it, but for this question, we're going to assume a confidence level of 95%. So confidence level is 0.95. Okay, so now that we have this, right, we want to estimate the we want to estimate the sample size needed. So we know that the margin of error is going to be equal to z star times the square root of p hat 1 minus p hat over n. And now you may ask, how do we know what our sample size is if we haven't found it? Well, in this case, we're going to make an assumption that we're going to assume normality checks pass for the sake of simplicity, right? And maybe the t star could be used in this case, but in this case, for sake of simplicity, I'm going to assume that the normality checks pass so that we're using the z distribution. And now that we know that our confidence level is 0.95, we know that this area in red is going to be 0.95. So that means this area in green is going to be 0.05 divided by 2. And this area here will be 0.05 divided by 2. So now what we want to do is find the z naught such that the probability of getting a z score less than or equal to negative z naught equals 0.05 divided by 2. So we use our z table. So we know that 0.05 divided by 2 is 0.025. So we need to look in this table and look for where 0.025 appears. And we see here that 0.025 appears right when z is negative 1.96. So in this case, we know that z naught equals 1.96. So z star will equal 1.96. So we know the margin of error is 0.03. We know that the z star is 1.96. And inside our square root, we know that p hat is 0.5 by assumption. And then 1 minus p hat has to be 0.5. And then our goal is to solve for n. So I need to solve this equation here for n, right? But we'll do a little algebraic manipulation. So we see that 0.03 over 1.96 equals the square root of 0.5 times 0.5 over n. And then when we square both sides, we see that 0.03 over 1.96 squared is going to be equal to 0.5 times 0.5 over n. So from this, we can rearrange and solve. So we'll see that n is equal to 0.5 times 0.5 over 0.03 over 1.96. That quantity is going to be squared. So I need to solve this. So I'm going to punch this to my calculator, and we'll see that our sample size is approximately our sample size is approximately 1067.11. So we need to sample approximately 1067 voters in order to estimate our true proportion of voters who support the new bill in our state within 3 percentage points using a 95% confidence level. So that seems like a lot of voters we need to collect samples for, right? So the accuracy and the narrowness of our confidence interval really depends on our confidence level. It also really depends on our standard deviation, which is influenced by p hat, as you saw in this example. And sometimes when we make conservative estimates, we're almost like estimating a worst case scenario in this case. So at the worst case, we'll have to sample approximately 1,067 voters in order to estimate the true proportion of voters who support the bill within 3 percentage points of accuracy. So I think that kind of seems like an interesting application of confidence intervals for proportions. Thank you very much for watching this video. Hopefully you got a good refresher or your memories jogged on confidence intervals for proportions and means. Hope to see you in the next video. Till then, tune in for the next one. Have a good rest of your night.